In this illustration, we'll find out the equivalent capacitance for a cube-shaped circuit. So here we'll study capacitors connected in form of cube. The first case here we are going to discuss, where it is saying figure shows 12 capacitors connected in form of a cubical frame. Here each capacitor is of capacitance C, and we are required to determine the equivalent capacitance of the frame across terminals A and G. Now in this situation, here if we use nodal analysis, we can connect a battery of 100 volt across the circuit. And in this situation, here we can see the potential on the terminal G is taken to be 0, then potential at terminal A will be 100 volt. Now in this situation, if we just have a look, the potential at this point is 100, here it is 0. So by symmetry on these three nodes, the potential must be same. Say we mark it X, X and X. Here I am taking all three as X because of symmetry, as these three nodes are at the same separation from 0 as well as 100. So by input and output symmetry, whichever charge the battery will pull from these three plates, that is going to be supplied on these three plates. As the capacitances are equal, the potential difference across these three must be same as that of these three. So here potential will be 100 minus X. Here also it is 100 minus X. And here also this 100 minus X. Now I can easily calculate the value of X by writing an equation for this node or any node at X. Potential is there. And then I can calculate the charge flown through the battery, which is delta QF, the sum of the charges on any of the sides of the battery. So here if we write the equation for X, from this X, three plates are connected. So charge on this plate is Cx plus charge on this plate is C multiplied by X minus 100 plus X plus charge on this plate is again X minus 100 plus X is equals to 0. Here C gets cancelled out. So it is giving us 5X is equals to 200. So the value of X here is 40 volt. If we have got the value of X, this charge flown through battery can be given as delta QF, which is equals to Cx plus Cx plus Cx, this 3Cx. So if we substitute the value of X, this 120C, that is a charge which is flown through the battery. So C across terminals A and G can be given as delta QF divided by 100. So this 120C by 100, the numerical value is 6C by 5. That is the answer to this problem. Let us discuss the alternative method for the same problem, which we have discussed in previous problem also. By potential distribution, if we consider here potential is 100 volt and here potential is 0 volt. And by symmetry, we have distributed potentials here as X, X and X. And on these three terminals, potential will be 100 minus X, 100 minus X, and here also it is 100 minus X. And by joining of equipotential points, we have discussed that if these three terminals are connected to each other, there won't be any charge flow in these because these are at same potential. So here we can consider these three capacitors C, C and C can be considered in parallel combination. So its equivalent capacitance will be 3C. Similarly, if we join these three terminals of 100 minus X to each other, these three capacitors will also be taken in parallel. So its equivalent will also be 3C. And remaining 1, 2, 3, 4, 5, 6 capacitors can also be taken in parallel because each of these 6 capacitors are connected with one terminal to this 100 minus X and other terminal to X. So this equivalent capacitance will become 6C. So if we draw its reduced equivalent circuit, then it will look like this. From terminal A, there is a capacitor of capacitance 3C, which represents the combination of these three. Then there is a capacitor of capacitance 6C, which represent the middle 6 capacitors, and then onward again a 3C capacitor. across terminal G. Now here we can directly write 1 by C equivalent across A and G can be written as 1 by 3C plus 1 by 6C plus 1 by 3C, which is 5 by 6C. So here C equivalent we are directly getting as 6C by 5. So this is the answer to this problem. But you must be very careful, as the use of this method requires a lot of practice. Unless the method is in your practice and you're confident, do not use it. Otherwise, you'll commit mistakes in your problems.